If you go to a tutor to learn how to do this kind of problem, or a person who's had some algebra and is pretty good at it, you'll find faster ways to do this kind of problem. But the way I'm showing you is the safest. It gives the best results. It leads to the best understanding. And if you go on in mathematics, it lets you become much better at this because of that understanding. And so what I think that you really ought to do is break apart the 45 to do its prime factorization. 45 is 9 times 5, and 9 is 3 times 3. So we have that the square root of 45 is the same thing as the square root of 3 times 5. Then we can break apart the product, the square root of a product, into the product of the square roots. As long as we're dealing with positive numbers, we can do that. And now this is not really a calculation. By definition, the square root of 3 is something you can multiply by itself and get 3. And so these two, when multiplied together, pair up and give us exactly 3. And we have this little leftover square root of 5, and we're done. This and this are the same thing. And this approach, in my opinion, is excellent. Now, admittedly, this is a lot of work to write this out, but it is the safest way to do it, and it's the easiest way to understand. And on an exam, it doesn't take very long, and you can be precise and accurate. But more importantly than that, if these numbers, these exponents, instead of 5 and 6 and 10, were 500 and 600 and 1,000, having done this a few times would let you deal with those bigger exponents in an easy, logical, straightforward manner. So I've broken this apart. The cube root of a product of a bunch of stuff is the product of the separate cube roots. And now what is true about cube roots? What is true specifically about the cube root of x? What is its claim to fame? Its claim to fame is that if you multiply 3 of them together, you get a plain ordinary x. So that's going to be an x. And then there's going to be a couple leftover ones. I'm going to circle the leftover ones. These 3 are going to make a y. These 3 are going to make a y, regular y's. No leftover cube roots of y. These 3 are going to make a z. These 3 are going to make a z. These 3 are going to make a z. And there's a leftover. So the leftovers look like this. Now, some of the rules of simplification are we use exponents when we can. So we have an x, and then we have a y squared, y times y. And we have a z cubed. And we have one leftover bin that contains all 3 of these parts. Instead of x times x, we're going to write x squared. And then we have a z. So these are the regular pieces out in front of the cube root. These are the things in the leftover bin. That took us a little while, and there is a way to look at this and write this down. But if you don't practice this by breaking them apart for quite a while, you're skipping some steps that'll come back and haunt you eventually. So make sure that you've written these out enough to where you're rock solid sure what you're doing. Otherwise, just gladly write it all out and count them up. So continue on using the same principle. Break the 10 apart into the square root of 5 times 2. Now, the square root of this product can be written as the product of the square roots. This times this is just plain 5. That's what it means to be a positive square root of 5. It's a number you can multiply by itself to get 5. And that's just a leftover square root of 2. It's unmatched, so it just stays itself. And we're done. Not too hard. So we're going to do the prime factorization of this number 9. It's 3 times 3. So this is the cube root of 3 times 3 times the cube root of 3. The cube root of a product is the product of the cube roots. And so what we're really looking at in this problem is 3 like cube roots multiplied together. But what is this cube root of 3? It's something you can multiply by itself 3 times and get exactly 3. And here we're multiplying it by itself 3 times, so we get exactly 3, and that's the answer, and we're done.